Hello everyone, I am Raza Abbas and now I am going to explain Cocotb. Cocotb stands for Coroutine Based Post Simulation Test Bench. It's Python framework used to verify hardware design which is written in Verilog and SystemVerilog. In this presentation I will cover the basic through some real example so it's suitable whether you are completely new or already know the fundamentals. Here I will cover the first fundamental. What is Cocotb? Why Python used for RTL verification. Then architecture and flow, how it's actually built. Then first working test bench example, which is 2x1 marks. And after that, who routine works and how actually run a test. Then simulator support and Cocotb compare with UVM. And finally test bench architecture. Now see what is Cocotb. It's a free open source framework which allows us to verify RTL design entirely in Python instead of Verilog and SystemVerilog. There is a term coroutine based. Coroutine is a special Python function which can be pause and resume according to the timing construct which is used inside the Python function. In normal Python function when we write, it starts from def keyword and function name. While when we write coroutine, it starts from a keyword async. It stands for asynchronous because in normal Python function we cannot use a timing construct, but in coroutine we use timing construct and it can be pause and resume from the same point. Next is co-simulation. Co stands for together. So in Python, in Cocotb, Python and simulator run together. That's why it's called co-simulation. Test bench environment for driving the stimulus. Here no RTL change. Look. Traditionally when we write test bench, there is a dot. Generally we write that in Verilog or SystemVerilog. And test bench could be in Verilog, SystemVerilog and UVM. When we write test bench in Cocotb, there is a dot. We do not change the language of dot. It means when dot is as it is written in Verilog or SystemVerilog. But when we write test bench, it must be in Python for Cocotb verification. Test bench must be written in Python language. And the next point is a test bench just a Python function. There is a decorator. I will explain it further. Simulation agnostic. It means Cocotb is independent of simulator. Python can communicate with different type of simulator using a GPI interface. It's a generic programming interface. I will explain it further. Using this GPI, Python can communicate with simulator and it is free open source. Let's move further. Let's see why brings Python into RTL verification. Traditionally we write test bench in Verilog, SystemVerilog and often in UVM. Learning UVM at the beginning level is difficult because it requires a lot of concepts. A small pool of engineers fluent in SystemVerilog and UVM when we compare with general software engineers. There is a limited access of software libraries. Let's talk about Cocotb. In Cocotb, we write test bench entirely in Python. It's the world's most widely known language. There is a full access of Python libraries, and it is readable code, easy to debug. Still uses a real HDL simulator. It means Cocotb does not replace the simulator, it replaces the test bench language. Before going further, here is some terminology like that, design under test. This is actual hardware. We write test bench in Cocotb to verify this data. Then test bench. There is Python code for driver, monitor and checker. Coroutine. It's a special Python function which can be pause and resume. Trigger. It's a timing construct which is used to advance the simulation time. Simulator. This is a actual engine which run the RTL, and it could be Questa, VCS, Xilium, Verilator, Icarus and so on. GPI, Generic Programming Interface. As I told you earlier, Python cannot communicate with simulator directly. We need GPI to communicate with simulator. I will explain the complete flow in next slide. Before moving further, let me explain some more terms like GPI. GPI stands for Generic Procedural Interface. When we install Cocotb, GPI install with it, and it's like inbuilt with Cocotb. GPI is used to call simulators interface, and there is 3 simulator interface. First one is VPI. VPI stands for Verilog Procedural Interface. Verilog Procedural Interface. Then VHPI. VHPI stands for VHDL Procedural Interface. Then FLI. Foreign Language Interface. Foreign Language Interface. This interface is like a door opened by simulator to communicate with outside language like Python. And VHPI is supported by Icarus and Verilator simulator. These are free source. And VHPI, Questa Sim and Xilium VCS also support VHPI, but generally for Questa commercial simulator like Questa Sim VCS Xilium supports FLI interface. We use FLI interface. Now let's see how they are linked each other. Suppose I have written my test bench in Python. I want to drive signal on my DUT, and my DUT is 2 cross 1 mux. There is 3 input signal A, B and select line. There is output Y. DUT dot A dot value equals to 1. DUT dot P dot value equals to 0. I want to drive these signals on my DUT. As we know, Python cannot directly communicate with a simulator. So there is Cocotb having GPI interface. Simulator supports suppose the simulator support VPI interface. VPI interface. In order to drive the signal on my RTL, GPI calls VPI interface, and VPI having three handle: VPI put value, VPI get value, and VPI register CB, register callback. To write the signal on RTL, we use VPI put value, and if we want to read the signal from RTL, then VPI use VPI get value. And if in my test bench there is any timing construct like await rising edge or timers, then my Cocotb just pause and control goes to simulator through VPI register callback. And once event has occurred, like for rising edge, if the clock changes to 0 to 1, then simulator callback, and again control goes to Python, and Cocotb resume as it is after that timing construct. And finally, through this simulator, write the signal on my RTL. Then this is a complete flow to drive or if to write or read the signal from simulator. Let's see next slide. See Cocotb architecture and flow. Python test at the top. In my test bench, there is decorator, which is used to mark our coroutine as a test or register coroutine as a test. Then Cocotb framework. Then GPI. GPI calls VPI interface. And finally, simulator applies the signal on RTL. Execution flow. In my test bench, there is timer. From that timer, the control goes back to the simulator. Simulator just advance the timing as much we have assigned and update the signal. And after that, there is simulator callback. Control again goes to Python, and my coroutine resume at the same point where it pauses. Then Python drives that signal test assert. Now see next. See on right side there is simple 2 corresponding marks RTL, and on left side there is Cocotb test bench. First line import Cocotb. This is used to import complete Python library, and next line is from cocotb.trigger import timer. This is used to cocotb.trimmer is a module used to import timer, rising edge, falling edge, and read only. In my test, I have used timer. That's why I have imported timer. Next line at the rate cocotb.test. This is a decorator. This is used to marks this coroutine as a test or register this coroutine as a test. As I told you, coroutine is just a Python function which can be paused or resumed. There is a dot handle. This dot handle is provided by simulator to access the RTL signal. Then now I am driving this signal on my RTL. I already explained you how this value changing on my RTL using simulator interface VPI put value. The next await timer. From this line, this coroutine just pauses and control goes back to the simulator. And after 1 nanosecond, there is Python callback and control goes back to Python. Then only the next line will execute. This await timer is just used to advance simulation time. Assert dot value equals to 0. This is self-checking. dot dot y dot value give the output value of y, and this is my actual value, and I am self checking here with expected value equals to 0. 0 is my expected value, and dot value dot y dot value give me actual value from the dot. This is assertion. If this y value equals to 0, assertion will pass, otherwise it will fail in result assertion error. This is how a simple test bench write in Cocotb. Now next, move on next slide. See, Cocotb timing construct group into three types. First one is timer. Like await, timer, 10 comma units equals to nanoseconds. It means it pause or suspend the coroutine until 10 nanoseconds of simulation time. It just advance simulation time for 10 nanoseconds. Second one is age trigger. Like rate rising age, dot clock, same as rate, falling age, dot clock. It paused the coroutine until this signal event. That means if for rising age, clock must be go from 0 to 1, then only coroutine will resume. And for falling age, clock will go from 1 to 0, then only coroutine will resume. The next one is read only. See. Third one is read, write, or read one. It is different from timer and rising age. It waits for a simulator scheduling phase and don't resume until the simulator has completed signal updation for this time is spent. It is very useful for monitor or scoreboarding where we need for final updated value. It's like read only, write only. So these are timing construct which is used in Cocotb Python test bench. Now move on next slide. As we know, Cocotb is coroutine based. It means Python does not run continuously. It just pause and resume from where it left off. When a wait keyword is triggered, control goes back to the simulator, and once event has occurred, control goes back to the Python and resume it from where it left off. Now we see a Verilog construct which is equivalent in Cocotb. In Verilog, we use at the rate pauses clock to wait for next positive edge clock. Similarly, we use await rising edge dot clock in Cocotb. Same for falling edge. Has 10 delay. This is a fixed simulation delay we use in Verilog test bench. Same in Cocotb we use this. Await time 10 nanoseconds. For 5 positive edge clock, waiting for 5 positive edge clock in Verilog, same as in Cocotb like this. Now move on next slide. Let's see another example of Cocotb test bench. In this case, our That is a counter. As we know, counter counts the clock pulse. Let's see from first line. Import Cocotb. It import Python library and package and give access to a decorator and connect us with the dot handle. Next is Cocotb.trigger import rising edge. Cocotb.trigger is a submodule which is used to import rising edge. And Cocotb.clock is also submodule which is used to import clock class, and that clock class further we use to create or generate clock pulse. From Cocotb xi dot import xi bus. This is used to import xi RAM model. If any xi master in our DUT, then it connects with the RTL signal. Then decorator. Decorator is used to register our coroutine as a test. Here asynchronous def counter dot handle. This is dot handle provided by our simulator to access dot signal. Cocotb dot start soon. This is a Cocotb function which run independently in the background, and it's used to generate clock pulse of 20 nanosecond. Time period will be 20 nanosecond. Drive the stimulus onto the DUT. First reset, we are asserting reset signal, then await. When this await trigger, control goes to the simulator, and once next clock has come, control there is Python simulator callback, and control goes back to the Python, and after this statement will execute, that is deassert our reset signal. Then there is a loop which is used to run our clock pulse for 10 times. This loop will run from 1 to 10, and there is assert signal dot count dot value equals to 10. This loop will execute 10 times. Then there will be 10 clock pulses. Our counter counts 10 clock. Then the actual value that will give 10, and the expected value will be 10. If this will be 10, count will be 10, then assertion will pass, otherwise it will fail. In case if assertion will fail, we'll get a message of mismatch. Cocotb test marks coroutine as a test. Asynchronous def await rising dot value is used to write and read the RTL signal. Now move on next slide. In order to run our test bench, we need makefile. Makefile just tells the Cocotb about the simulator name, top level language. That means in which language we have written our DUT, Verilog files, name of our DUT, name of our test bench, then finally include. Now see, as we know, Cocotb supports almost every simulator. It's communicate with simulator via interface. There is VPI interface for Verilator and VPI for Icarus Verilog, Vesta, FLI and VPI also support. VCS, Xilium. I already explained this. Now move on next slide. Now see, difference between Cocotb and UVM. In Cocotb, if you know Python, then you can easily write test bench in Cocotb. While in UVM, before writing test bench in UVM, you must know SystemVerilog classes, macros, and phasing all of this. In Cocotb Python modules packages, UVM based library classes factory. Cocotb having its inbuilt debugger, while in UVM it's simulator dependent. Every simulator having its own debugger. Cocotb is now growing and UVM is mature. It's a industry standard. Cocotb rising and it's dominant. Main difference about simulator cost. Cocotb also supports free simulator like iCares Verilog and Verilator, while UVM effectively needs commercial tool. This is Cocotb test bench structure. There is test which drive the test sequence, and driver just pushes that sequences to the DUT using interface. Monitor observe the DUT signal, and finally scoreboard compare expected and actual values and produce pass and fail. This is project layout. There is RTL, RTL DUT module, and test bench. There is test bench for DUT, driver, monitor, scoreboard, reference, and coverage. And after this, there is 5. Then our test bench. Here is driver, monitor, and scoreboard. Driver convert transaction into pin level signals and implement handshake protocol. And monitor is just reverse of driver. Monitor convert pin level signals into transaction, and it is passive component. It means do not apply any signal. It's just monitor the DUT. And finally, it sends transaction to scoreboard for comparing expected and actual data. And scoreboard is comparing expected versus actual and generate pass and fail counting and final report. See, this is a summary of Cocotb. Cocotb is used to verify our DUT, which have written in Verilog and SystemVerilog, and we write Cocotb test bench in Python. There is a GPI which acts as a bridge between Python and simulator, which communicate with simulator interface, and it supports 10 plus simulator. Tests are asynchronous coroutine. Python pauses on trigger and resume when the simulator fires them. It fits right into your existing Python toolbox, no new ecosystem to learn. Best suited for protocol level verification. Today it's fast growing ecosystem, closing gap with UVM. Thank you everyone.